Hello there, and welcome to the Dreamy Science Channel. I'm so glad you found your way here tonight. Maybe you've been looking up at the stars wondering about distant worlds. Or perhaps you simply need something gentle and fascinating to help your mind unwind. Either way, you're in exactly the right place. Tonight, we're going to explore one of humanity's most remarkable achievements. A telescope so advanced, it has changed how we see the universe itself. There's nothing you need to do but rest. Let your breathing slow, your thoughts soften, and your body settle into comfort. Because tonight, we're drifting through the quiet wonders of the James Webb Space Telescope. This isn't just any telescope. It's a delicate miracle floating in the darkness of space, sending us images and discoveries that feel almost like dreams. Some of what you'll hear tonight may surprise you. Other facts might simply flow by like gentle whispers, soothing and quietly unforgettable. And if these peaceful explorations help you rest or spark your curiosity, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let's begin this gentle journey through the cosmos. The James Webb Space Telescope is larger than a tennis court when fully deployed. Imagine something so vast, it could cover an entire tennis court. Yet so delicate it must unfold like an origami flower in the silence of space. The James Webb Space Telescope spans over 21 meters from end to end when its solar panels and instruments are fully extended. This enormous size isn't for show. Every square meter serves a purpose, collecting precious sunlight to power its systems and providing the stability needed for observations that require the steadiness of a surgeon's hand. The telescope had to be folded like a complex puzzle to fit inside the rocket that carried it to space. Watching it unfold was like witnessing a mechanical ballet, each movement precise and graceful, revealing the full majesty of human engineering floating against the star-filled void. The telescope's mirror is made of 18 hexagonal segments that work as one. At the heart of the James Webb Space Telescope lies its primary mirror, a golden masterpiece composed of 18 individual hexagonal pieces. Each segment is about the size of a coffee table, but together they create a single, perfect mirror over 6 meters across. These segments aren't just placed side by side. They're aligned with a precision that defies imagination, positioned to within nanometers of their ideal locations. The entire surface is smoother than anything you could achieve by hand, smoother than the calmest lake on a windless morning. When light from distant stars and galaxies hits this mirror, it's gathered and focused with such accuracy that the telescope can see details that would be invisible to any other instrument ever built. The mirror's golden coating isn't just beautiful. It reflects infrared light perfectly, allowing Webb to capture the warm glow of objects billions of light years away. James Webb sits at a gravitational balance point, 1.5 million kilometers from Earth. The telescope doesn't orbit Earth like the Hubble Space Telescope. Instead, it rests at a special location in space called the second Lagrange point, or L2. This is a place where the gravitational pull of Earth and the Sun balance perfectly, creating a stable parking spot in the cosmic void. At this distance, roughly 4 times farther than the Moon, the telescope can observe the universe without Earth's heat interfering with its sensitive instruments. It's like having a quiet observatory in the middle of nowhere, far from the lights and warmth of home. From this vantage point, Webb can see the entire night sky as it slowly rotates around the sun, never blocked by Earth's shadow, always bathed in the gentle light of distant stars. The journey to reach this point takes about a month, a careful drift through the darkness until the telescope finds its perfect home in space. The telescope operates at temperatures colder than anywhere on Earth. To see the universe's faintest infrared light, the James Webb Space Telescope must be incredibly cold. Its instruments operate at temperatures around -233 degrees Celsius, colder than the surface of Pluto, colder than any natural place in our solar system. This extreme cold is maintained by a sun shield the size of a tennis court, a delicate barrier with 5 layers that block the heat from the sun, Earth, and Moon. Each layer is thinner than human hair, yet together they reduce the temperature by hundreds of degrees. The sun shield works like a cosmic umbrella, creating a permanent shadow where the telescope's instruments can operate in perfect darkness. Without this protection, the telescope's own heat would overwhelm the faint signals it's trying to detect. It's remarkable to think that in the depths of space, human technology has created one of the coldest places in the known universe. Every image from Webb is actually invisible to human eyes. The James Webb Space Telescope doesn't see the universe the way we do. Instead of visible light, it detects infrared radiation, the warm glow that objects emit even in the darkness of space. This invisible light carries stories that visible light cannot tell. It can pierce through cosmic dust clouds that would otherwise hide distant stars and galaxies. It can reveal the heat signatures of planets orbiting other stars. It can even show us the stretched light from the most ancient galaxies, light that has been traveling toward us since the universe was young. When we see Webb's stunning images, we're looking at invisible light translated into colors our eyes can appreciate. Red might represent one type of infrared emission, blue another. The telescope acts as a translator, converting the universe versus hidden conversations into a language of light and shadow that speaks to our souls. The telescope can see galaxies forming just after the Big Bang. One of Webb's most extraordinary abilities is its power to look back in time. Because light takes time to travel across the vast distances of space, when we look at distant objects, we see them as they were long ago. The James Webb Space Telescope can detect light that has been traveling toward us for over 13 billion years. Light that began its journey when the universe was still a child. These observations show us galaxies in the process of forming, stars igniting for the first time, and cosmic structures taking shape in an era when the universe was very different from today. It's like having a time machine that doesn't take us to the past, but brings the past to us. In Webb's images, we can see the universe learning how to make stars, how to build galaxies, how to become the cosmic home we know today. Each photon of ancient light is a message from a time before planets, before complex chemistry, before life itself. Webb's instruments are so sensitive they could detect a candle on one of Jupiter's moons. The sensitivity of the James Webb Space Telescope is almost beyond comprehension. Its instruments can detect individual photons, the smallest possible units of light, arriving after journeys of billions of years through space. To put this in perspective, if you lit a single candle on one of Jupiter's moons, Webb could see that tiny flame from Earth. This extraordinary sensitivity allows the telescope to study objects that are incredibly faint and distant. It can analyze the atmospheres of planets orbiting other stars, looking for the chemical signatures that might indicate the presence of water, oxygen, or even life itself. It can peer into the hearts of distant galaxies and watch black holes consume matter. It can study the birth of stars in regions so dark and dusty that no other telescope can see through them. Every observation is a testament to human ingenuity and our deep desire to understand the cosmos. The sun shield had to unfold perfectly, or the mission would have failed. Perhaps no part of the James Webb Space Telescope's deployment was more nerve-wracking than the unfolding of its sunshield. This enormous structure, composed of 5 ultra-thin layers, had to deploy flawlessly in the vacuum of space with no possibility of repair. The sunshield is held in place by hundreds of pulleys, cables, and mechanisms, each one crucial to the telescope's success. The unfolding process took weeks and had to happen in a precise sequence. First, the telescope extended its supporting booms, then carefully separated each layer of the sunshield, stretching them tight like the sails of a cosmic ship. Engineers on Earth could only watch and wait as their carefully designed mechanisms worked in the silent darkness of space. There was no room for error, no second chances. The fact that everything worked perfectly is a quiet miracle of engineering and planning. The sunshield now floats in space like a giant silver butterfly, protecting the telescope's instruments and enabling discoveries that continue to astonish us. Each mirror segment can be adjusted individually while in space. The 18 hexagonal segments of Webb's primary mirror aren't fixed in place. Each one can be moved and tilted with incredible precision using tiny motors called actuators. This allows engineers to fine-tune the telescope's vision even after it has traveled millions of kilometers from Earth. The alignment process is like focusing a camera, but infinitely more complex. Each segment must be positioned to work in perfect harmony with its neighbors, creating a single, flawless mirror surface. The actuators can move each segment by distances smaller than the width of a human hair, making adjustments that ensure every photon of light is captured and focused exactly where it needs to go. This capability means that Webb can maintain its perfect vision throughout its mission, compensating for the tiny changes that occur as the telescope experiences the thermal cycling of space. It's like having a telescope that can constantly adjust its own prescription glasses. The telescope's main camera weighs less than a grand piano, but costs more than some countries' entire budgets. The near-infrared camera, or NIRCAM, is Webb's primary imaging instrument. Despite weighing only about 390 kilograms, roughly the same as a grand piano, this sophisticated device represents one of the most expensive cameras ever built. Its development required years of research and testing, pushing the boundaries of detector technology to create sensors capable of seeing the universe's faintest light. Every component had to be designed to work flawlessly in the extreme conditions of space, from the bitter cold of deep space to the radiation environment far from Earth's protective atmosphere. The camera contains multiple detector arrays, each one calibrated to detect specific wavelengths of infrared light. When you see those breathtaking images of distant galaxies and nebulae, you're looking at the work of this remarkable instrument, translating invisible light into visible beauty with a precision that borders on the miraculous. Webb can analyze the chemical composition of atmospheres around distant planets. One of the telescope's most exciting capabilities is its ability to study the atmospheres of planets orbiting other stars. When a planet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching Webb's sensitive instruments. By analyzing this filtered light, scientists can identify the chemical elements and compounds present in that distant atmosphere. The telescope can detect water vapor, carbon dioxide, methane, and other gases that might indicate whether a planet could support life as we know it. This process is like reading a chemical fingerprint written in starlight, decoding messages that have traveled across dozens or even hundreds of light years. Each observation brings us closer to answering one of humanity's most pressing questions. Profound questions. Are we alone in the universe? The telescope's ability to study these distant worlds represents a new chapter in our search for life beyond Earth. The telescope's journey to its operating position was like threading a cosmic needle. Getting the James Webb Space Telescope to its destination at the L2 Lagrange point required a journey of extraordinary precision. Unlike launching a satellite into Earth orbit, this mission required threading a cosmic needle, following a carefully calculated path through the gravitational fields of Earth, Moon, and Sun. The spacecraft had to travel for about a month, making course corrections along the way to ensure it arrived at exactly the right location with exactly the right velocity would overshoot its target. Too slow, and it would never arrive. Too fast, and it. The journey was like a cosmic ballet, choreographed years in advance and executed with split-second timing. Throughout the trip, the telescope's instruments remained protected behind its sun shield, staying cold and safe during the long drift through space. When it finally reached L2, the telescope performed a final maneuver to insert itself into a gentle orbit around this invisible point in space, where it now floats in perfect balance, ready to explore the universe. The telescope's mirrors were polished to a smoothness that defies comprehension. Each of Webb's 18 mirror segments underwent a polishing process that took months to complete. The final surface of each mirror is so perfectly smooth that if it were scaled up to the size of Earth, the largest imperfection would be only 6 feet tall. This level of precision is achieved through a combination of traditional optical techniques and cutting-edge technology. The mirrors were shaped using computer-controlled polishing machines that could remove material one atom at a time. During the process, engineers used laser interferometry to measure the surface accuracy, checking for deviations smaller than the wavelength of light itself. The result is a collection of mirrors so perfect they seem almost otherworldly, each one a testament to human patience and precision. When starlight hits these flawless surfaces, it bounces back with virtually no distortion, preserving every detail of the cosmic scenes Webb observes. The telescope's pointing system is more stable than a surgeon's steadiest hand. To capture clear images of distant objects, the James Webb Space Telescope must hold incredibly still while observing. Its pointing system can lock onto a target and maintain that position with an accuracy of 1/100th of an arcsecond. To put this in perspective, this level of precision would allow you to hold a laser pointer steady enough to illuminate the same spot on a coin from 40 kilometers away. This stability is achieved through a combination of reaction wheels, gyroscopes, and fine guidance sensors that constantly monitor and adjust the telescope's orientation. The system can compensate for the tiny vibrations caused by the telescope's own electronics, the thermal expansion and contraction of its structure, and even the minute gravitational influences of distant celestial bodies. This remarkable steadiness allows Webb to take long exposure images, collecting photons over hours or even days to reveal the universe's faintest secrets. Webb's spectrographs can identify individual chemical elements across billions of light years. Hidden within the telescope's instrument bay are sophisticated devices called spectrographs that break light apart into its component colors, much like a prism separates white light into a rainbow. These instruments can detect the unique spectral signatures of different chemical elements, revealing the composition of objects throughout the universe. When Webb observes a distant star, its spectrographs can identify not only hydrogen and helium, but also trace amounts of heavier elements like carbon, oxygen, and iron. This capability extends far beyond our own galaxy, allowing scientists to study the chemical evolution of the universe itself. The telescope can detect elements in galaxies so distant that their light began traveling toward us when the universe was less than 1 billion years old. Each spectrum is like a chemical census, telling us what the universe was made of at different epochs in cosmic history. The telescope operates on less power than a household hairdryer. Despite its incredible capabilities, the James Webb Space Telescope consumes remarkably little power. Its entire suite of instruments and systems runs on less than 2,000 watts, about the same amount of electricity as a typical hairdryer. This efficient design was crucial because the telescope must generate all its power from solar panels while operating in the cold depths of space. The power management system is a marvel of engineering, carefully distributing electricity to each instrument and system while maintaining the precise temperature control needed for infrared observations. Every component was designed with efficiency in mind, from the low-power electronics that control the mirror segments to the cryogenic cooling systems that keep the instruments at their operating temperature. This frugal use of power ensures that Webb can operate continuously for many years, sending back a steady stream of discoveries without interruption. The telescope's data travels across space at the speed of light, but takes time to reach us. Every image and spectrum that Webb captures must travel 1.5 million kilometers from the telescope to Earth, a journey that takes about 5 seconds at the speed of light. The telescope communicates with Earth through the Deep Space Network, a collection of large radio antennas located around the globe. Each day, Webb transmits dozens of gigabytes of data, enough information to fill thousands of high-resolution photographs. This data stream includes not only scientific observations, but also engineering information about the telescope's health and status. The communication system must work flawlessly because there's no way to physically retrieve data from Webb or repair its systems if something goes wrong. Every bit of information is precious, carrying within it the potential for discoveries that could reshape our understanding of the universe. Webb can see objects that are moving away from us faster than any earthly vehicle. Due to the expansion of the universe, some of the most distant galaxies Webb observes are receding from us at speeds that dwarf anything we can imagine on Earth. These galaxies are moving away at tens of thousands of kilometers per second, velocities that stretch their light toward longer, redder wavelengths. This stretching, called cosmological redshift, actually helps Webb observe these ancient systems because it shifts their originally visible light into the infrared wavelengths where the telescope excels. The faster a galaxy is moving away from us, the more its light is stretched, and the further back in time we're seeing it. Some of Webb's most distant targets are receding so quickly that their light has been stretched by a factor of 10 or more, transforming blue starlight into deep infrared radiation that only Webb's sensitive detectors can perceive. The telescope's instruments can detect temperature differences smaller than a degree on distant planets. Webb's infrared capabilities extend beyond simply seeing distant objects. The telescope can measure incredibly subtle temperature variations across the surfaces of planets orbiting other stars. When these worlds pass behind their host stars as seen from Earth, Webb can detect the slight drop in infrared light as the planet's warm day side disappears from view. By analyzing these tiny changes in brightness, scientists can map temperature patterns across alien worlds, revealing whether they have atmospheres, weather systems, or even day-night temperature cycles. This thermal mapping capability works across interstellar distances, allowing us to study the climate patterns of worlds that are dozens of light years away. Each observation adds another piece to our growing understanding of how planets form and evolve throughout the galaxy. The telescope's flight software contains over 2 million lines of code. Behind Webb's graceful operation in space lies an incredibly complex software system that controls every aspect of the telescope's behavior. This flight software, containing more than 2 million lines of carefully written and tested code, manages everything from pointing the telescope at specific targets to controlling the temperature of individual instruments. The software must operate flawlessly in the harsh environment of space, where there's no possibility of a technician arriving to fix problems. Every line of code was reviewed multiple times, tested in simulated space conditions, and verified to work correctly under all possible scenarios. The software includes sophisticated algorithms for image processing, autonomous target acquisition, and fault detection. It's like having a highly intelligent robotic assistant that never sleeps, constantly monitoring the telescope's health and making adjustments to ensure optimal performance. Webb's mirrors were tested in conditions that simulate the vacuum of space. Before launch, every component of the James Webb Space Telescope underwent extensive testing in facilities that replicate the extreme conditions of space. The mirrors were tested in enormous vacuum chambers, cooled to temperatures approaching absolute zero, mimicking the environment they would experience at the L2 Lagrange point. These tests required specialized equipment, capable of creating and maintaining conditions colder and emptier than any natural place on Earth. Engineers observed how the mirrors behaved as they cooled, measuring tiny changes in their shape and position. The testing revealed that the mirrors would contract and slightly change shape as they reached their operating temperature, information that was crucial for programming the alignment procedures that would be performed after launch. These ground-based tests provided confidence that Webb's optical system would work perfectly in space, even though the mirrors had never been tested as a complete assembly under space conditions. The telescope can observe the same region of sky for days without interruption. Unlike ground-based telescopes that must pause their observations when the sun rises, Webb can stare at the same patch of sky for extended periods, limited only by the need to occasionally point its solar panels toward the sun for power. This capability allows the telescope to perform ultra-deep observations, collecting photons over many hours or even days to reveal objects too faint to be seen in shorter exposures. During these marathon observing sessions, Webb's instruments accumulate light from some of the most distant and ancient objects in the universe, building up detailed images and spectra photon by precious photon. The telescope's stable orbit around L2 means that it never has to deal with the day-night cycle that constrains Earth-based astronomy. Instead, it operates in a realm of perpetual night, where the only illumination comes from distant stars and the faint glow of cosmic background radiation. Each of Webb's infrared detectors is more sensitive than photographic film by millions of times. The heart of Webb's incredible sensitivity lies in its state-of-the-art infrared detectors, devices so advanced they can register individual photons arriving from the depths of space. These detectors are millions of times more sensitive than traditional photographic film and thousands of times better than the detectors used in earlier space telescopes. Each detector array contains over 2 million individual pixels, and every pixel can measure the energy and arrival time of incoming infrared photons with extraordinary precision. The detectors are cooled to just a few degrees above absolute zero, reducing thermal noise to almost nothing and allowing them to detect the faintest cosmic whispers. Manufacturing these detectors requires techniques borrowed from the semiconductor industry, creating devices so pure and perfect that they respond to individual packets of light that have traveled billions of years to reach them. The telescope's gyroscopes can detect motion smaller than the width of a human hair. Webb's ability to point accurately and hold steady depends on a set of ultra-precise gyroscopes that can sense incredibly small rotational movements. These devices can detect changes in the telescope's orientation that correspond to movements smaller than the width of a human hair at a distance of 10 kilometers. This exquisite sensitivity allows Webb's guidance system to make continuous tiny adjustments, keeping the telescope locked onto its targets with unwavering precision. The gyroscopes work in conjunction with star trackers, devices that identify patterns of bright stars and use them as reference points for navigation. Together, These systems create a guidance capability so accurate that Webb can track objects as they move across the sky, following planets, asteroids, or comets, while maintaining perfect focus throughout long observational sequences. Webb's orbit around L2 takes it on a gentle dance through space. The telescope doesn't simply park at the L2 Lagrange point, like a car in a cosmic parking space. Instead, it follows a complex orbital path around this invisible gravitational balance point, tracing out a route that takes about 6 months to complete. This orbit is carefully designed to keep the telescope in constant communication with Earth, while ensuring that it never passes into Earth's shadow, which would block sunlight from reaching its solar panels. The orbital motion is so gentle that it requires only tiny amounts of fuel to maintain, allowing Webb to operate for decades on the propellant it carries. From Earth's perspective, the telescope appears to drift slowly across a small region of sky, always positioned where it can observe the universe without interference from the Sun, Earth, or Moon. This cosmic choreography ensures that Webb remains in the perfect location for astronomical discovery. The telescope's cooling system is more precise than maintaining the temperature of a single snowflake. Keeping Webb's instruments at their operating temperature requires a cooling system of extraordinary precision. The telescope must maintain temperatures within tiny fractions of a degree, controlling thermal conditions more precisely than preserving a single snowflake in a warm room. This is achieved through a combination of passive cooling from the sunshield and active cooling systems that use helium gas to reach the final operating temperatures. The cooling process happens gradually over months, allowing each component to shrink and settle into its final configuration as the temperature drops. Engineers can monitor and adjust this cooling from Earth, fine-tuning the thermal environment to optimize the telescope's performance. The result is an instrument suite that operates in a state of perfect thermal stability, where every observation benefits from conditions that remain constant to within the smallest measurable amounts. Webb's primary mirror collects light that has been traveling since before Earth formed. Some of the photons that Webb captures began their journey across the universe more than 4.5 billion years ago, before our solar system existed. These ancient particles of light have been traveling through expanding space, carrying information from a time when the Milky Way was younger and the universe looked very different. When these photons finally strike Webb's golden mirrors, they complete journeys that span not just vast distances but immense periods of time. The telescope serves as a collector of cosmic history, gathering light that witnessed the formation of the first galaxies, the birth of early stars, and the gradual chemical enrichment of the universe. Each observation is like receiving a message in a bottle that has been floating across the cosmic ocean for billions of years. The telescope can measure distances to galaxies with the precision of measuring the length of a football field from space. Webb's ability to determine cosmic distances relies on identifying specific types of stars and phenomena whose true brightness is known. By comparing how bright these objects appear to how bright they actually are, astronomers can calculate their distance with remarkable precision. This capability allows Webb to measure distances to galaxies millions of light-years away with an accuracy comparable to measuring the length of a football field from orbit around Earth. These precise distance measurements help scientists understand how fast the universe is expanding, how galaxy clusters are moving, and how cosmic structures have evolved over time. Each distance measurement adds another data point to our three-dimensional map of the universe, revealing the large-scale architecture of cosmic space. Webb's instruments were assembled in clean rooms, thousands of times purer than hospital operating theaters. The construction of Webb's delicate instruments required facilities cleaner than any environment on Earth outside of specialized laboratories. These clean rooms maintain air purity levels thousands of times better than hospital operating theaters, removing virtually every speck of dust, every stray particle that might contaminate the telescope's sensitive components. Workers wore special suits and followed strict protocols to prevent any contamination from reaching the instruments. Even microscopic particles invisible to the naked eye could interfere with Webb's observations, so the assembly process took place in environments where the air itself was continuously filtered and purified. The instruments were handled with tools designed never to touch their surfaces directly, ensuring that when Webb finally began observing the universe, its detectors were pristine and ready to capture the faintest cosmic light. The telescope's reaction wheels store and release energy like a cosmic flywheel system. To change its pointing direction without using precious fuel, Webb relies on 4 spinning wheels called reaction wheels. These devices work on the principle of conservation of angular momentum, speeding up or slowing down to torque the entire telescope in the opposite direction. The reaction wheels can store rotational energy like flywheels, allowing Webb to slew from target to target with smooth, precise movements. When the wheels eventually become saturated with too much stored momentum, the telescope uses its thrusters to desaturate them, transferring the excess angular momentum to its orbital motion around L2. This elegant system allows Webb to point anywhere in the sky with minimal fuel consumption, preserving its propellant supply for the small adjustments needed to maintain its orbit over many years of operation. Webb can detect infrared light that has been stretched by cosmic expansion for over 13 billion years. The most distant objects Webb observes emit light that has been stretched by the expansion of the universe to such an extent that radiation originally emitted in visible wavelengths now arrives as infrared. This stretching, known as redshift, increases with distance and time, meaning that the most ancient galaxies Webb studies appear in the deepest infrared wavelengths. The telescope's instruments are specifically designed to detect this highly redshifted light, allowing astronomers to see galaxies as they appeared when the universe was less than 1 billion years old. Each photon of this ancient light carries information about conditions in the early cosmos, revealing how the first stars formed, how early galaxies assembled, and how the chemical elements that make life possible were first created and distributed through space. The telescope's star trackers use constellation patterns to navigate like ancient seafarers. Webb navigates through space using a modern version of celestial navigation, employing star trackers that identify patterns of bright stars and use them as reference points. These sophisticated cameras continuously photograph the star field around the telescope, comparing what they see to onboard catalogs containing the positions of thousands of guide stars. By recognizing these stellar patterns, Webb always knows exactly which direction it's pointing and can slew to new targets with extraordinary accuracy. The star trackers work like digital sextants, using the fixed positions of distant stars as a cosmic compass that never fails. This navigation system operates continuously, providing the pointing accuracy needed for Webb's most demanding observations, while requiring no external signals or ground-based assistance. Webb's sunshield materials are thinner than human hair, yet stronger than steel. The 5 layers of Webb's sunshield are made from a specialized material called capton, each layer thinner than a human hair, but engineered to be stronger than steel when properly supported. These gossamer-thin membranes must survive the launch environment, deployment in space, and years of thermal cycling as the telescope orbits L2. Each layer serves a specific function in the thermal protection system, reflecting and absorbing different wavelengths of solar radiation to create the temperature gradient that keeps Webb's instruments cold. The sunshield layers are coated with aluminum and silicon to enhance their reflective properties, creating a barrier that reduces the temperature behind the shield by hundreds of degrees. Despite their delicate appearance, these layers represent some of the most advanced materials engineering ever achieved, combining lightness with durability in a way that enables Webb's revolutionary capabilities. The telescope can observe atmospheric dynamics on worlds orbiting other stars. Beyond detecting the chemical composition of exoplanet atmospheres, Webb can study their weather patterns and atmospheric circulation. By monitoring how the infrared emission from these distant worlds changes over time, astronomers can track storm systems, temperature variations, and even the movement of cloud formations across alien skies. This capability extends our understanding of planetary science beyond the solar system, revealing how atmospheres behave on worlds with different masses, compositions, and orbital characteristics. Some exoplanets show dramatic temperature variations between their day and night sides, while others appear to have efficient heat transport that creates more uniform temperatures. Each observation adds to our knowledge of planetary atmospheres as a class of objects, helping us understand both the uniqueness of Earth's climate system and the diversity of atmospheric phenomena throughout the galaxy. Webb's fine guidance system can lock onto targets smaller than a grain of sand seen from across a city. The telescope's fine guidance sensors provide pointing stability so precise they could track an object the size of a grain of sand from a distance of several kilometers. This extraordinary precision is essential for Webb's most demanding observations, such as studying the atmospheres of planets orbiting other stars, or tracking the proper motion of distant objects over time. The guidance system uses dedicated guide stars to maintain perfect pointing throughout long observations, continuously making tiny adjustments to compensate for any drift or vibration. This stability allows Webb to perform spectroscopy on incredibly faint targets, collecting light over many hours while maintaining perfect alignment between the target and the instrument's entrance aperture. The precision of this system represents one of the most challenging aspects of Webb's engineering, requiring components that can maintain their accuracy in the harsh environment of space. The telescope's data processing systems can analyze light that carries the signatures of cosmic dawn. Webb's onboard computers and ground-based data processing systems work together to extract scientific information from the faint light of the most distant observable objects. These systems can identify spectral features that reveal the presence of the first heavy elements created by early stars, trace the ionization of hydrogen in the early universe, and measure the properties of galaxies that formed when the cosmos was still emerging from its dark ages. The data processing involves sophisticated algorithms that can separate genuine cosmic signals from instrumental artifacts, calibrate observations to account for the telescope's response characteristics, and combine multiple exposures to build up detailed images and spectra of incredibly faint targets. Each processed observation represents the distillation of millions of individual photon detections into scientific knowledge about the universe's earliest epochs. Webb's instruments can detect the thermal glow from objects barely warmer than the cosmic microwave background. The telescope's infrared sensitivity extends to detecting thermal emission from objects that are only slightly warmer than the cosmic microwave background radiation itself, the faint afterglow of the Big Bang that permeates all of space. This extreme sensitivity allows Webb to study cold objects like brown dwarfs, planetary debris disks, and the outer regions of solar systems, where temperatures drop to just tens of degrees above absolute zero. The instruments can distinguish between objects that differ in temperature by just a few degrees, revealing thermal structures and processes that were previously invisible to astronomical observation. This capability opens up entirely new categories of cosmic phenomena for study, from the coolest failed stars to the icy outer reaches of planetary systems throughout the galaxy. The telescope's mirror alignment system can make adjustments smaller than a virus. Each of Webb's 18 primary mirror segments can be positioned with an accuracy smaller than the size of a typical virus. This nanometer precision alignment is achieved through actuators that can move the mirrors in incredibly small increments, finer than any mechanical system ever deployed in space. The alignment process involves analyzing the light from bright stars to determine exactly how each mirror segment needs to be adjusted to work in perfect harmony with its neighbors. This process, called wavefront sensing, can detect optical imperfections smaller than the wavelength of light itself and correct them by moving the mirrors accordingly. The result is a telescope mirror that performs better than any single large mirror could, combining the light-gathering power of its full 6.5-meter aperture with optical quality that approaches the theoretical limits of perfection. Webb's orbital mechanics allow it to observe any point in the universe without obstruction. The telescope's position at L2 and its carefully designed orbit ensure that it can point to any location in the sky without being blocked by the sun, Earth, or Moon. This complete sky access is crucial for studying transient phenomena, following up on discoveries made by other observatories, and conducting comprehensive surveys of different regions of the universe. Unlike telescopes in Earth orbit that have viewing restrictions due to our planet's shadow or the sun's glare, Webb operates in a location where the entire cosmos is accessible for observation. The telescope can even observe the same target continuously for extended periods, building up incredibly detailed observations of objects that vary in brightness or spectral characteristics over time. This unrestricted access to the sky makes Webb an ideal platform for discovering and studying the universe's most elusive phenomena. The telescope's thermal management system maintains temperature stability better than any laboratory on Earth. Webb's ability to maintain stable temperatures across its instrument suite exceeds the capabilities of even the most advanced terrestrial laboratories. The telescope's thermal control systems can detect and correct temperature variations of a few thousandths of a degree, ensuring that the instruments operate in conditions of unprecedented stability. This thermal precision is achieved through a combination of passive design elements, active heating systems, and sophisticated control algorithms that continuously monitor and adjust temperatures throughout the observatory. The stable thermal environment is crucial not only for the sensitivity of Webb's infrared detectors, but also for maintaining the precise alignment of its optical components over the years-long duration of its mission. This thermal stability represents one of the most demanding engineering challenges overcome in Webb's development. Webb's communication system can transmit data across space with less power than a cell phone tower. Despite being nearly 1.5 million kilometers from Earth, the James Webb Space Telescope maintains constant communication using transmitters that consume less power than a typical cellular base station. The telescope's high-gain antenna can beam data back to Earth with remarkable efficiency, focusing its radio signals like a cosmic flashlight pointed directly at our planet. This communication link carries not only the scientific observations that astound us daily, but also the continuous stream of engineering data that tells mission controllers about every aspect of the telescope's health and status. The radio waves carrying Webb's discoveries travel at the speed of light. But even at that incredible velocity, they take several seconds to bridge the gap between the telescope and the deep space network antennas that receive them. Each transmission represents a bridge between the silence of deep space and the eager anticipation of scientists and engineers waiting to decode the universe's latest secrets. The telescope's spectrographs can split starlight into over 100,000 individual colors. Hidden within Webb's instrument bay are spectrographs so sophisticated they can separate light into components far beyond what any prism or rainbow could reveal. These devices can divide the light from a single star or galaxy into more than 100,000 distinct wavelengths, each carrying specific information about the object being observed. This incredible spectral resolution allows astronomers to identify not just which chemical elements are present in distant objects, but also their temperatures, densities, magnetic field strengths, and motions through space. When Webb observes a galaxy billions of light years away, its spectrographs can detect the subtle Doppler shifts that reveal how fast different parts of that galaxy are rotating. The presence of shock waves from exploding stars, and even the rate at which new stars are forming in its spiral arms. Each spectrum is like a detailed medical examination conducted across impossible distances, revealing the vital signs of cosmic objects through the language of light. Webb's detectors can count individual photons that began their journey before multicellular life evolved on Earth. Some of the light particles that Webb's sensitive detectors capture started their cosmic voyage more than 1 billion years ago, when Earth was populated only by single-celled organisms and complex life had yet to emerge. These ancient photons have been traveling through expanding space for eons, carrying within them the signatures of stars and galaxies from a universe very different from the one we see today. When these particles of light finally reach Webb's detectors after their billion-year journey, they trigger electronic signals that are amplified, digitized, and transmitted back to Earth, where they become part of humanity's growing understanding of cosmic evolution. Each detected photon represents a connection across deep time, linking the present moment with epochs when the universe was younger, more turbulent, and filled with the first generation of massive stars that would seed space with the heavy elements necessary for planets and life. The telescope's pointing accuracy is equivalent to hitting a golf ball on the moon from Earth. Webb's ability to point precisely at celestial targets reaches a level of accuracy that seems almost magical. The telescope can aim its instruments at objects in space with a precision equivalent to striking a golf ball placed on the lunar surface using a club swung from Earth. This extraordinary pointing capability is achieved through a combination of star trackers, gyroscopes, and fine guidance sensors working together in perfect harmony. The system can not only point to incredibly small targets, but also track them as they move across the sky, compensating for the telescope's own orbital motion and the apparent movement of objects due to Earth's rotation around the Sun. This precision is essential for studying small, faint objects like distant asteroids, the moons of other planets, or the cores of galaxies where supermassive black holes lurk. Without this accuracy, Webb's most ambitious observations would be impossible, like trying to thread a needle while wearing thick gloves. The telescope's cryogenic cooling system operates more quietly than a whisper in space. Webb's cooling systems maintain the frigid temperatures necessary for infrared observations while operating in complete mechanical silence. Unlike terrestrial refrigeration systems that rely on compressors and moving parts, Webb's cooling is achieved through passive radiative cooling and closed-cycle refrigerators that have no vibrating components. This silent operation is crucial because even the tiniest vibrations could blur the telescope's images or interfere with its precise measurements. The cooling systems work continuously, removing heat generated by the telescope's electronics and maintaining each instrument at its optimal operating temperature. The thermal management is so sophisticated that different instruments can be maintained at different temperatures simultaneously, with some components kept at just a few degrees above absolute zero, while others operate at slightly warmer temperatures. This multi-temperature environment is maintained with a precision that would be challenging to achieve in the best laboratories on Earth. Webb's solar array generates power more efficiently than any earthbound solar installation. The telescope's solar panels convert sunlight into electricity with an efficiency that surpasses most terrestrial solar installations, despite operating in the harsh radiation environment of space. These panels are designed to maintain their performance over many years of exposure to cosmic radiation, temperature cycling, and micrometeorite impacts. The solar array can automatically track the Sun as Webb orbits around L2, ensuring optimal power generation throughout the telescope's complex orbital dance. The power system includes sophisticated batteries that store energy during periods when the telescope's instruments require maximum power for observations, then recharge when power demands are lower. This electrical system must operate flawlessly because there's no possibility of repair or replacement once Webb is in space. Every component was tested extensively on Earth to ensure it could provide reliable power for the telescope's decade-long mission. The telescope can measure the wobble of stars caused by planets smaller than Earth. Webb's incredible sensitivity extends to detecting the tiny gravitational influences that small planets exert on their host stars. When a planet orbits a star, it causes that star to wobble slightly, shifting back and forth by distances smaller than the width of a building. These minuscule movements can be detected by Webb through precise measurements of the star's spectrum, looking for the Doppler shifts that reveal the star's motion toward and away from us. This technique allows the telescope to discover planets that are too small and dim to be seen directly, including rocky worlds that might be similar to Earth. The measurements require such precision that Webb can detect velocity changes of just a few meters per second in stars that are dozens of light years away. Each successful detection adds another world to our catalog of exoplanets and brings us closer to understanding how common Earth-like worlds might be throughout the galaxy. Webb's instruments operate in a vacuum so perfect it surpasses any laboratory on Earth. The space around Webb's instruments represents one of the most perfect vacuums ever achieved, with a particle density far lower than anything that can be created in terrestrial laboratories. This ultra-high vacuum is maintained naturally by the telescope's location in deep space, far from any atmosphere or outgassing materials. The vacuum is so complete that gas molecules might travel for kilometers before encountering another particle, creating an environment where thermal conduction is virtually non-existent. This perfect vacuum is essential for Webb's thermal control systems, allowing different components to be maintained at vastly different temperatures without unwanted heat transfer. The instruments operate in this pristine environment without any possibility of contamination from atmospheric particles, moisture, or chemical vapors that would interfere with sensitive infrared observations. It's an environment so pure that it approaches the theoretical ideal of empty space itself. The telescope's guidance system can track objects moving slower than a snail's pace across the sky. Webb's fine guidance sensors can detect and compensate for motions so subtle they would be imperceptible to human observation, tracking objects that drift across the sky at rates slower than a garden snail moves across the ground. This capability is crucial for studying objects within our own solar system, such as asteroids, comets, and the moons of distant planets, which appear to move against the background stars due to their orbital motion. The telescope can lock onto these moving targets and follow them smoothly for hours or days, maintaining perfect tracking while its instruments collect detailed observations. This tracking ability extends to objects throughout the solar system and beyond, allowing Webb to study everything from near-Earth asteroids to Kuiper Belt objects at the very edge of our planetary system. The precision of this tracking system ensures that even during long exposures, moving targets remain perfectly centered in the telescope's field of view. Webb's thermal shields create temperature differences greater than the span between boiling water and liquid nitrogen. The temperature difference between the sun-facing and space-facing sides of Webb's sunshield represents one of the most extreme thermal gradients ever engineered into a space system. The sun-facing side of the shield reaches temperatures hot enough to melt lead, while just a few meters away, the space-facing side maintains temperatures colder than liquid nitrogen. This enormous temperature difference is achieved through the careful design of the shield's 5 layers, each one precisely positioned to absorb, reflect, or transmit specific amounts of thermal energy. The gradient is so steep that you could theoretically place a thermometer on one side of the shield that reads over 300 degrees Celsius, while another thermometer just a short distance away would register nearly 200 degrees below zero. This thermal engineering marvel enables Webb's instruments to operate in their required cryogenic environment, while the rest of the telescope basks in the full intensity of solar radiation. The telescope's mirror segments were manufactured with precision exceeding atomic dimensions. Each of Webb's 18 mirror segments was crafted with a surface accuracy that approaches the limits of what's physically possible, with deviations from the ideal shape measuring less than the size of individual atoms. This level of precision was achieved through advanced manufacturing techniques that combine traditional optical polishing with modern computer-controlled systems capable of removing material at the molecular level. The manufacturing process required months of careful work for each segment, with continuous monitoring using laser interferometry to ensure that every surface remained within specifications. Even microscopic imperfections that would be invisible under the most powerful microscopes were detected and corrected during the manufacturing process. The result is a collection of mirror segments so perfectly formed that they can focus starlight with virtually no distortion, preserving every detail of the cosmic scenes Webb observes across billions of light-years of space. Webb's reaction wheel system can change the telescope's orientation using less energy than lifting a paperclip. The telescope's ability to rotate and point to different targets in space is achieved through a reaction wheel system so efficient it consumes less energy than would be required to lift a single paperclip against Earth's gravity. These spinning wheels can store and release rotational energy with remarkable efficiency, allowing Webb to slew from one target to another using only tiny amounts of electrical power. The system operates on the principle of conservation of angular momentum, speeding up or slowing down the wheels to generate the torques needed to rotate the entire telescope. This elegant approach means that Webb can perform hundreds of pointing maneuvers using the same amount of energy that powers a small light bulb for preserving the telescope's limited, of this system is crucial: a few minutes. The efficiency needed for its diverse observational programs. The telescope can power budget while maintaining the pointing edge, detect infrared radiation from objects cooler than Antarctic, extends to detecting thermal emission from objects with ice. Webb's infrared sensitivity temperatures far below anything found naturally on Earth's surface, including regions colder than the most frigid Antarctic conditions. This capability allows the telescope to study cold brown dwarfs, icy bodies in the outer solar system, and the frigid gas and dust clouds where new stars are born. The telescope can measure temperature differences of just a few degrees in objects that are already hundreds of degrees below freezing, revealing thermal structures and processes that would be completely invisible to optical telescopes. This sensitivity to cold objects opens up new categories of astronomical phenomena for study, from failed stars that never achieved nuclear fusion to the icy debris disks surrounding young stars where planets may be forming. Each observation of these cold objects adds to our understanding of how matter behaves in the extreme conditions found throughout the universe. Webb's computer systems process more information per second than 1,000 home computers combined. The telescope's onboard computers and data processing systems handle information at rates that dwarf the capabilities of typical personal computers, processing and formatting observations for transmission to Earth, with computational power equivalent to thousands of home systems working together. These computers must operate reliably in the radiation environment of space, using specially hardened processors and memory systems that can withstand cosmic rays and solar particle events. The computational systems handle everything from pointing the telescope and controlling its instruments to formatting scientific data and managing communications with Earth. The software running on these systems represents millions of lines of carefully tested code, designed to operate autonomously for years, making complex decisions about scheduling observations, managing power consumption, and responding computational capability ensures that Webb can operate to unexpected situations. This as an intelligent, autonomous observatory of observing time. The telescope's infrared, making optimal use of every second detectors, can sense heat signatures across interstellar distances. Webb's ability to detect infrared radiation extends far beyond simple temperature measurements, allowing signatures and thermal processes across the telescope to map heat interstellar distances. The detectors can distinguish between different sources of infrared emission, whether from stellar surfaces, warm dust clouds, or the thermal glow of distant galaxies. This thermal mapping capability reveals processes that would be completely hidden in visible light observations, such as starulae, or the heat formation occurring deep within dusty neb generated by matter falling into supermassive black holes. The telescope can even detect the waste heat from advanced civilizations, should such signatures exist, by looking for artificial infrared emissions that differ from natural astrophysical sources. Each infrared observation adds another dimension to our understanding of cosmic processes, revealing the universe as a dynamic thermal environment where energy flows and transforms across to entire galaxy clusters. Webb scales from individual stars' orbital position, provides a view of the universe unobstructed by any natural satellite or planetary body. Unlike telescopes operating from Earth's surface or in Earth orbit, Webb enjoys a completely unobstructed view of the entire cosmos from its position at L2. The telescope never has to contend with Earth's shadow, the Moon's interference, or atmospheric absorption that limits ground-based observations. This complete sky access means that Webb can observe any astronomical target at any time, limited only by the need to keep the sun behind its protective sunshield. The telescope can follow transient events like supernovae or gamma-ray bursts for extended periods, building up detailed observations as these cosmic explosions evolve over time. This unrestricted access to the sky makes Webb an ideal platform for time-domain astronomy, studying how celestial objects change and evolve over periods, ranging from minutes to years. The telescope's location in space provides a stable, unvarying platform for observations that would be impossible from any other vantage point. The telescope's alignment system can correct optical errors smaller than the wavelength of the light it collects. Webb's active optic system can detect and correct optical imperfections that are smaller than the wavelength of the infrared light the telescope is designed to observe. This correction capability is achieved through a sophisticated wavefront sensing system that analyzes the light from bright stars to determine exactly how the telescope's optics are performing. When minute imperfections are detected, the system can command the primary mirror segments to adjust their positions by distances measured in nanometers, correcting optical errors that would otherwise limit the telescope's performance. This active correction system ensures that Webb maintains optimal optical quality throughout its mission, compensating for any changes that might occur as the telescope's structure thermally equilibrates in space or experiences the subtle effects of solar radiation pressure. The result is a telescope that performs better than would be possible with any fixed optical system, achieving image quality that approaches the fundamental limits imposed by the wave nature of light itself. Webb's data storage systems can hold the equivalent of over 1 million high-resolution photographs. The telescope's onboard data storage capabilities represent a remarkable feat of space-qualified electronics, capable of holding scientific observations equivalent to millions of high-resolution digital photographs. This storage capacity is essential because Webb often observes targets that are only visible for limited periods, requiring the telescope to collect and store data when observations are possible and transmit it to Earth when communication windows allow. The storage systems use advanced solid-state memory technology designed to operate reliably in the radiation environment of space, with built-in error correction and redundancy to ensure that precious scientific data is never lost. The systems can simultaneously store new observations while transmitting previously collected data to Earth, managing the complex flow of information that represents humanity's expanding knowledge of the universe. Each stored observation represents hours of careful planning and represents irreplaceable scientific data that may never be collected again if lost. The telescope's sunshield deployment required over 300 individual mechanisms to work perfectly in sequence. The successful deployment of Webb's sunshield represents one of the most complex mechanical operations ever performed in space. requiring more than 300 separate mechanisms to operate flawlessly in a precisely choreographed sequence. Each mechanism had to work perfectly on its first attempt, with no possibility of repair or reset if something went wrong. The deployment process involved extending support booms, separating sunshield layers, tensioning cables, and positioning the entire assembly with millimeter precision. Every step of the process was monitored from Earth through several seconds to travel telemetry signals that took from the telescope to mission control, meaning that by the time engineers received confirmation of each step, the next steps were already underway. The successful completion of this deployment sequence represents a triumph of engineering planning and execution, enabling Webb's flawless operation of hundreds scientific mission through the of individual components working together in the silent vacuum of space. Webb can simultaneously observe multiple targets while maintaining perfect focus on each one. The telescope's sophisticated optical design allows it to observe several different astronomical targets simultaneously, maintaining perfect focus and tracking on each object while collecting data with multiple instruments. This multiplexing capability dramatically increases Webb's scientific efficiency, allowing astronomers to study comparative samples of similar objects or monitor multiple targets for variability and changes over time. The telescope can split its attention between nearby and distant objects, studying everything from asteroids in our own solar system to galaxies at the edge of the observable universe during the same observing session. This parallel processing capability is made possible by Webb's multiple instruments and sophisticated pointing system, which can maintain the precise alignment needed for each observation while compensating for the different apparent motions of targets at vast, simultaneously different distances. Each observation represents an optimization of the telescope's precious observing time, maximizing the scientific return from every moment spent in space. The telescope's field of view can capture an area of sky equivalent to holding a grain of sand at arm's length. Despite its enormous mirror and sophisticated optics, Webb's field of view is remarkably small when compared to the vastness of the night sky. The telescope's most detailed observations cover an area roughly equivalent to what you would see if you held a single grain of sand at arm's length against the starry backdrop. This narrow field of view is actually a strength rather than a limitation, allowing Webb to concentrate its light-gathering power and achieve unprecedented detail in its observations. The small field size means that every photon collected represents an incredibly concentrated sample of cosmic information, packed with details about distant objects that would be completely lost in wider field observations. This focused approach allows the telescope to peer deeper into space and further back in time than would be possible with instruments designed to survey larger areas of sky. Each narrow field observation is like examining the universe through a cosmic microscope, revealing intricate structures and processes that exist on the smallest observable scales. Webb's fine guidance sensors can detect stellar motion smaller than the apparent size of a quarter on the moon. The telescope's ability to track and guide on stellar targets reaches levels of precision that challenge human comprehension. The fine guidance sensors can detect movements of guide stars that correspond to angular changes smaller than the apparent size of a coin viewed on the lunar surface from Earth. This extraordinary sensitivity allows Webb to maintain perfect pointing stability even when observing the faintest and most distant objects, ensuring that long exposures accumulate light from exactly the intended targets. The guidance system continuously monitors multiple guide stars simultaneously, using their apparent positions to calculate and correct for any drift or rotation of the telescope's orientation. This precision is maintained throughout observations that may last for many hours, during which the telescope must compensate for its own orbital motion, thermal effects, and the subtle gravitational influences of celestial bodies. The result is a pointing stability that enables Webb to perform observations that would be impossible with less precise guidance systems. The telescope's spectrometers can analyze light that has been traveling through space longer than complex life has existed on Earth. When Webb studies the most distant galaxies, it analyzes light that began its journey when the universe was a fraction of its current age, and Earth was still a world of simple, single-celled organisms. These photons have been stretching and cooling as they traveled through expanding space for billions of years, carrying within them information about cosmic conditions that existed long before multicellular life emerged on our planet. The spectrometers can extract detailed information from this ancient light, revealing the chemical composition that existed when the universe was fundamentally different from what we temperature and physical conditions of objects observed today. Each spectrum represents a direct connection to cosmic history, allowing present-day scientists to study the universe as it appeared during epochs that predate not only human civilization, but the evolution of complex life itself. This temporal reach makes Webb not just a telescope, but a time machine that brings the deep past into direct contact with the present moment. Webb's thermal control systems maintain temperature stability better than the most precise laboratory freezers. The telescope's ability to maintain consistent temperatures across its instrument suite exceeds the capabilities of even the most advanced cryogenic systems used in terrestrial research facilities. The thermal management systems can detect and respond to temperature variations of thousandths of a degree, ensuring that the sensitive infrared detectors operate in conditions of unprecedented stability. This precision is achieved through a combination of passive thermal design, active heating elements, and sophisticated control algorithms that continuously monitor and adjust temperatures throughout the observatory. The stable thermal environment is crucial not only for detector sensitivity, but also for maintaining demanding observations. Temperature fluctuations that the precise optical alignment needed for Webb's MOST would be imperceptible to human sensation could significantly degrade the telescope's performance, making this thermal control system one of the most critical aspects of the observatory's design. The result is an instrument platform that maintains more consistent operating conditions than any laboratory facility on Earth. The telescope can detect chemical signatures in the atmospheres of worlds orbiting stars invisible to the naked eye. Webb's spectroscopic capabilities extend to analyzing the atmospheric composition of planets orbiting stars so faint they cannot be seen without telescopic assistance. When these distant worlds pass in front of their host stars, the telescope can detect the subtle absorption lines created as starlight filters through alien atmospheres. This technique allows astronomers to identify specific molecules and compounds in the air of worlds that are dozens or hundreds of light-years away, revealing whether they contain water vapor, carbon dioxide, methane, or other gases that might indicate habitability or even biological activity. The precision required for these measurements is extraordinary, as the atmospheric signals represent tiny fractions of the total light received from these distant stellar systems. Each successful atmospheric analysis adds another entry to our growing catalog of exoplanet environments, helping scientists understand the diversity of atmospheric conditions that exist throughout the galaxy and assess the potential for life in other solar systems. Webb's primary mirror assembly weighs less than a small car, but focuses light with the precision of a perfect lens. The entire primary mirror system, including 18 segments, and they're as much as a compact supporting structures, weighs approximately automobile, yet delivers optical performance that exceeds what could be achieved by any single mirror of comparable size. This remarkable combination of low weight and high performance was achieved through advanced materials, engineering, and manufacturing techniques that pushed the boundaries of optical fabrication technology. Each mirror segment is made from beryllium, a metal chosen for its exceptional stiffness-to-weight ratio and thermal stability in cryogenic conditions. The segments are polished to perfection and coated with a thin layer of gold that optimizes their reflectivity for infrared wavelengths. Despite their gossamer weight, these mirrors can focus starlight with such precision that the resulting images are limited only by fundamental physical principles rather than manufacturing imperfections. This achievement represents decades of materials science research and optical engineering development. The telescope's communication system transmits discoveries across space using less power than a microwave oven. Despite the enormous distance between Webb and Earth, the telescope's high-gain antenna can beam scientific data and engineering telemetry back to our planet, using transmitters that consume less electrical power than a typical household microwave oven. This efficient communication system focuses radio waves into a narrow beam pointed precisely at Earth, maximizing the signal strength received by the deep space network antennas that capture Webb's transmissions. The radio link carries not only the spectacular images and spectra that capture public imagination, but also the continuous stream of engineering data that tells mission controllers about every aspect of the telescope's health and performance. Each transmission represents a bridge across the vast emptiness of space, carrying information that transforms our understanding of the cosmos from a location where human presence would be impossible. The efficiency of this communication system ensures that Webb can share its discoveries while conserving precious electrical power for its scientific instruments and operational systems. Webb's actuators can position mirror segments with precision smaller than a strand of DNA. The mechanical systems that control the position and orientation of each primary mirror segment operate with precision that approaches molecular dimensions, capable of making adjustments smaller than the width of a DNA double helix. These actuators respond to commands from the telescope's alignment system, making continuous tiny corrections that maintain perfect optical performance as the telescope experiences thermal changes and mechanical settling in the space environment. Each actuator can move its associated mirror segment in 6 different directions, providing complete control over position and orientation with nanometer precision. The actuators operate silently and smoothly, avoiding vibrations that could disturb the telescope's sensitive observations while maintaining the mirror alignment needed for optimal image quality. This precision mechanical control represents one of the most challenging aspects of Webb's engineering, requiring components that can maintain their accuracy over years of operation in the harsh conditions of deep space. The result is an optical system that can be continuously optimized for peak performance throughout the mission. The telescope's instruments can measure the polarization of light that has traveled across cosmic time. Beyond simply detecting and analyzing the brightness and spectrum of distant objects, Webb's instruments can measure the polarization characteristics of light that has journeyed across billions of years of cosmic history. Polarization analysis reveals information about magnetic fields, scattering processes, and geometric structures that cannot be obtained through conventional photometry or spectroscopy. When light from distant galaxies, nebulae, or other cosmic objects becomes polarized through interaction with magnetic fields or dust grains, it carries subtle signatures that Webb's sensitive polarimetry systems can detect and analyze. This capability allows astronomers to study phenomena such as the magnetic field structures around black holes, the alignment of dust grains in star-forming regions, and the polarization signatures that may have been imprinted on light during the universe's earliest moments. Each polarization measurement adds another dimension to our understanding of cosmic processes, revealing aspects of the universe that remain hidden to other observational techniques. Webb's cryocooler systems extract heat more efficiently than any refrigeration technology. Maintain Webb's instruments at their operating temperatures represent on Earth. The active cooling systems that the pinnacle of cryogenic engineering, achieving cooling efficiency that surpasses any terrestrial refrigeration system. These cryocoolers must operate continuously for years without maintenance, removing heat from the instrument compartments while generating no vibrations that could disturb the telescope's sensitive observations. The cooling systems use closed-cycle processes that require no consumable refrigerants, relying instead on carefully engineered thermodynamic cycles that can extract heat from already frigid components and reject it to the even colder environment of deep space. This thermal management is achieved through systems so efficient they can maintain temperature differences of hundreds of degrees across distances of just a few centimeters, creating precisely controlled thermal environments for each instrument. The reliability and efficiency of these cooling systems enable Webb to maintain its unprecedented infrared sensitivity throughout its planned mission duration and potentially far beyond. The telescope's orbital mechanics allow it to observe the same patch of sky continuously for months. Webb's unique orbital configuration around the L2 Lagrange point enables extended observations that would be impossible from any other location in space. The telescope can maintain its gaze on specific regions of the sky for months at a time, limited only by the need to occasionally adjust its orientation to keep its solar panels pointed toward the sun for power generation. This extended observing capability is crucial for studying phenomena that change slowly over time, such as the evolution of supernovae, the orbital dynamics of distant binary systems, or the seasonal variations in the atmospheres of exoplanets. The telescope's stable position in space means that it never has to interrupt observations due to Earth's rotation, atmospheric interference, or orbital constraints that limit other astronomical facilities. This continuous observing capability allows Webb to accumulate incredibly deep exposures of faint objects, building up detailed observations, photon by photon, over extended periods. The result is an unprecedented ability to study the universe's most elusive phenomena with a persistence that matches their cosmic timescales. Webb's navigation system uses the positions of distant quasars as cosmic lighthouses. The telescope's precision pointing and navigation capabilities rely partly on observations of distant quasars, supermassive black holes that shine with incredible brightness from the centers of galaxies billions of light years away. These cosmic beacons serve as fixed reference points that help define Webb's orientation in space with extraordinary accuracy. The quasars are so distant that they appear stationary relative to the telescope's motion, providing stable reference points that can be used to calibrate and verify the telescope's pointing system over long periods. This celestial navigation system operates alongside star trackers and gyroscopes to maintain the precision needed for Webb's most demanding observations. The use of quasars as navigation references represents a remarkable application of cosmological phenomena to practical engineering challenges, turning some of the universe's most energetic objects into tools for precise spacecraft control. Each navigation measurement connects Webb's immediate operational needs to the vast structure of the cosmos itself. The telescope's data compression algorithms can reduce file sizes while preserving every detail needed for discovery. Webb generates enormous amounts of scientific data that must be efficiently stored on board and transmitted to Earth across the vast distance to L2. The telescope's sophisticated data compression systems can reduce the size of observations by significant factors while preserving all the information needed for scientific analysis. These algorithms are specifically designed for astronomical data, understanding the statistical properties of cosmic signals and optimizing compression accordingly. The compression systems can distinguish between genuine astronomical signals and instrumental artifacts, preserving the former while efficiently encoding the latter. This intelligent data handling ensures that Webb can collect and transmit far more observations than would be possible with simple storage and communication systems. The compression algorithms represent years of development and testing, designed to operate reliably in the space environment, meant while maintaining the data integrity essential for groundbreaking discoveries. Each compressed observation represents an optimal balance between information content and transmission efficiency. Webb's structural design can withstand forces equivalent to sitting on top of a controlled explosion. The telescope's mechanical structure was designed to survive the intense vibrations and accelerations experienced during launch, forces equivalent to being positioned directly above a carefully controlled, but enormously powerful explosion. The launch environment subjects every component of the telescope to stresses, vibrations, and accelerations that far exceed anything experienced in normal Earth-based operations. Despite these extreme conditions, Webb's delicate instruments, precision optics, and gossamer-thin sunshield layers all survived the journey to space completely intact. The structural design required careful analysis of every component, ensuring that each element could withstand launch loads while maintaining the precision needed for subsequent space operations. This durability was achieved through advanced materials engineering, sophisticated structural analysis, and extensive testing that simulated the launch environment in Earth-based facilities. The successful survival of launch represents a triumph of mechanical engineering that enabled Webb's subsequent transformation into a precision scientific instrument operating in the gentle environment of deep space. The telescope can track asteroids moving through our solar system while simultaneously observing distant galaxies. Webb's sophisticated pointing and tracking systems enable it to follow moving targets within our solar system while maintaining the stability needed to observe fixed objects in deep space. This dual capability allows the telescope to study solar system objects such as asteroids, comets, and planetary moons, while also conducting observations of distant galaxies, nebulae, and other cosmic phenomena during the same observing sessions. The tracking systems can compensate for the apparent motion of solar system objects against the background stars, maintaining perfect focus and alignment throughout long observational sequences. This capability dramatically increases Webb's scientific efficiency, allowing astronomers to study both local and cosmic phenomena using the same precious observing time. The ability to seamlessly transition between tracking moving objects and observing fixed targets represents sophisticated control systems that can adapt to the diverse requirements of modern astronomy. Each tracking observation demonstrates the telescope's versatility as a tool for exploring phenomena across the entire range of cosmic distances. Webb's mirror coatings were applied with atomic-level precision in vacuum chambers cleaner than deep space. The gold coatings that give Webb's mirrors their distinctive appearance were applied using processes that achieve uniformity and precision at the atomic level. These coatings were deposited in vacuum chambers that maintain cleanliness levels exceeding even the vacuum of deep space, ensuring that no contaminants could interfere with the coating process or degrade the mirror's optical performance. Each mirror segment received a coating just a few hundred atoms thick, applied with such precision that the thickness varies by less than a single atomic layer across the entire surface. The gold coating process required specialized equipment and techniques developed specifically for Webb's unique requirements, combining traditional optical coating methods with cutting-edge vacuum technology and precision control systems. The resulting mirror surfaces reflect infrared light with nearly perfect efficiency, while maintaining their performance in the harsh radiation environment of space. These coatings represent one of the most precisely controlled manufacturing processes ever applied to space hardware. The telescope's gyroscopes can detect rotation rates slower than the hour hand of a clock. Webb's guidance system includes gyroscopes so sensitive they can measure rotational velocities far slower than the movement of a clock's hour hand, providing the precise angular rate information needed for accurate pointing control. These instruments can detect changes in the telescope's orientation that correspond to rotation rates measured in tiny fractions of degrees per hour, sensitivity that enables Webb to maintain stable pointing even in the face of subtle, disturbing forces. The gyroscopes work continuously throughout each observation, providing real-time information about the telescope's rotational state that allows the guidance system to make immediate corrections for any unwanted motion. This extreme sensitivity to rotation is achieved through advanced sensor technology designed specifically for space applications, combining precision manufacturing with sophisticated signal processing to extract useful information from incredibly small signals. The gyroscopic measurements are integrated with data from star trackers and other sensors to create a complete picture of the telescope's orientation and motion in space. Each measurement contributes to the precision that enables Webb's most demanding astronomical observations. Webb's power management system can allocate electricity with the precision of a master conductor directing an orchestra. The telescope's electrical systems distribute power throughout the observatory with a precision and coordination that rivals a symphony conductor managing dozens of musicians. The power management computers continuously monitor the electrical demands of every instrument, heater, motor, and electronic system aboard the telescope, adjusting the distribution of available electricity to ensure optimal performance of all components. This dynamic power allocation allows Webb to operate different combinations of instruments simultaneously while maintaining the thermal control and pointing stability needed for successful observations. The system can predict power requirements for upcoming observations and adjust the charging and discharging cycles of the telescope's batteries to ensure adequate electrical supply during periods of peak demand. This sophisticated electrical management represents years of systems engineering development, creating power distribution capabilities that optimize Webb's scientific productivity while protecting all systems from electrical anomalies or unexpected power demands. The telescope's sunshield layers are separated by gaps smaller than the thickness of paper, yet create temperature differences of hundreds of degrees. The 5 layers of Webb's sunshield are positioned with gaps between them that measure just a few millimeters, separations thinner than typical writing paper. Yet these tiny spaces enable temperature reductions of hundreds of degrees from one layer to the next. This remarkable thermal performance is achieved through careful design of each layer's optical properties and the precise control of the spacing between adjacent layers. The gaps between layers are maintained by a complex system of cables, pulleys, and tensioning mechanisms that keep each membrane at exactly the right distance from its neighbors. The thermal isolation provided by these narrow gaps relies on the vacuum of space, where heat transfer can occur only through radiation rather than conduction or convection. Each layer intercepts and redirects thermal energy from the sun, while allowing the space-facing side of the shield to radiate heat into the cosmic background. This layered thermal protection system creates one of the most effective thermal barriers ever engineered. Webb can measure the chemical composition of clouds of gas and dust that will someday become new solar systems. The telescope's spectroscopic instruments can analyze the chemical makeup of interstellar clouds, where future stars and planets are destined to form, revealing the raw materials available for planetary system construction throughout the galaxy. These observations provide insights into the chemical diversity of star-forming regions and help astronomers understand how the abundance of different elements influences the types of planets that can form in different galactic environments. Webb can detect the spectral signatures of molecules ranging from simple hydrogen and carbon monoxide to complex organic compounds that might serve as precursors to the chemistry of life. The telescope's sensitivity allows it to study these tenuous clouds across vast distances, mapping the chemical properties of stellar nurseries in our own galaxy and beyond. Each observation of these pre-stellar environments adds to our understanding of the conditions that lead to planetary system formation and the chemical evolution of galaxies over cosmic time. The ability to analyze the composition of future solar systems before they form represents a unique perspective on cosmic chemical evolution. The telescope's reaction wheels can spin for decades without maintenance, while maintaining precision better than a Swiss timepiece. Webb's attitude control system relies on spinning wheels that must operate flawlessly for the entire duration of the mission, maintaining rotational precision that exceeds the accuracy of the finest mechanical timepieces ever made. These reaction wheels are engineered to spin continuously for years without lubrication, adjustment, or any form of maintenance, using magnetic bearings and precision-balanced rotors that eliminate mechanical wear and friction. The wheels can store and release angular momentum with such precision that they enable Webb to point at targets with accuracy measured in tiny fractions of an arcsecond, while slewing smoothly between different observational targets. This mechanical precision is maintained in the harsh environment of space, where temperature variations, radiation, and micrometeorite impacts could potentially affect the performance of less robust systems. The reaction wheels represent decades of spacecraft engineering development, combining materials science, precision manufacturing, and advanced control systems to create components that operate reliably throughout extended space missions. Webb's optical design focuses starlight so precisely that diffraction creates perfect six-pointed patterns. When Webb observes bright stars, the telescope's hexagonal mirror segments and supporting struts create diffraction patterns that appear as perfect six-pointed star shapes in the resulting images. These diffraction spikes are not optical flaws, but rather signatures of Webb's unique optical design, created by the precise geometry of the primary mirror assembly and the telescope's structural elements. The patterns are so regular and predictable that they serve as indicators of the telescope's optical alignment and performance, with any deviations from the expected diffraction pattern revealing potential issues with mirror positioning or optical quality. The six-pointed diffraction spikes have become an iconic signature of Webb's images, distinguishing them from observations made by other telescopes with different optical configurations. Each perfectly formed diffraction pattern represents the constructive and destructive interference of light waves passing through the telescope's aperture. demonstrating the wave nature of light in the most visually striking way possible. The telescope's fine guidance sensor can detect stellar positions with accuracy equivalent to measuring the width of a human hair from 2 miles away. Webb's precision pointing capability relies on fine guidance sensors that can determine stellar positions with accuracy that defies ordinary comprehension, equivalent to measuring the diameter of a single hair from a distance of several kilometers. This extraordinary precision enables the telescope to lock onto guide stars and maintain perfect pointing throughout observations lasting many hours, compensating for thermal drift, mechanical settling, and the subtle gravitational influences that affect spacecraft in deep space. The fine guidance sensor continuously monitors the positions of multiple guide stars simultaneously, using their apparent locations to calculate and correct for any changes in the telescope's orientation. This real-time guidance system ensures that astronomical targets remain precisely centered in the telescope's field of view throughout long exposures, enabling Webb to collect the faint light from distant objects with maximum efficiency. The sensor's precision represents the culmination of decades of development in space-based guidance technology, creating capabilities that enable observations impossible with less accurate pointing systems. Webb's spectrometers can detect spectral lines so narrow they reveal the internal motions within distant galactic cores. The telescope's high-resolution spectroscopic capabilities extend to detecting incredibly narrow spectral features that reveal the detailed kinematics and physical conditions within the central regions of distant galaxies. These observations can map the motion of gas and stars around supermassive black holes, revealing the gravitational influences and accretion processes that occur in some of the most extreme environments in the universe. The spectral resolution achieved by Webb's instruments allows astronomers to measure velocity differences corresponding to just a few kilometers per hour second in objects located millions or billions of light-years away. This precision enables studies of galactic dynamics, stellar formation processes, and the physics of matter under extreme gravitational conditions. Each high-resolution spectrum provides a detailed view of cosmic processes that would remain hidden to lower-resolution instruments, revealing the complex interplay between gravity, radiation, and matter that shapes the evolution of galaxies throughout the universe. The telescope operates in an environment where the nearest solid surface is nearly 1.5 million kilometers away. Webb functions in a region of space more isolated than any human-made object has ever operated, floating in the vacuum with the nearest planetary surface nearly 1.5 million kilometers distant. This profound isolation means that the telescope must operate with complete autonomy, making decisions about its observations, thermal control, and system health without any possibility of direct human intervention. The nearest substantial gravitational influences come from Earth and the Sun, whose combined pull creates the stable Lagrange point where Webb maintains its position. In this cosmic isolation, the telescope experiences conditions of vacuum and radiation that cannot be fully replicated in any Earth-based testing facility. The successful operation of such a complex system in this remote environment represents an extraordinary achievement in autonomous spacecraft design and operation. Every component must function flawlessly because there is no possibility of repair, replacement, or direct assistance from the distant Earth that launched it into the cosmic void. Webb's thermal management creates microclimates more stable than any natural environment on Earth. The telescope's sophisticated thermal control systems create and maintain temperature environments more stable than any location found in nature on our planet. With variations measured in thousandths of degrees, rather than the degree scale fluctuations common in even the most thermally stable terrestrial environments. This unprecedented thermal stability is achieved through a combination of passive thermal design, active temperature control, and continuous monitoring systems that respond to thermal changes faster than they can affect the telescope's sensitive instruments. Different regions of the telescope maintain vastly different temperatures simultaneously, creating a complex thermal landscape where components just meters apart may differ in temperature by hundreds of degrees, while each maintains perfect stability within its designated range. This thermal engineering enables Webb's infrared instruments to detect the faintest cosmic signals while operating in conditions more controlled than the most advanced laboratory facilities on Earth. Each thermally controlled zone represents a precisely maintained microenvironment optimized for its specific function within the observatory's complex systems. The telescope's data processing capabilities can analyze observations faster than the light from those same objects can travel 1 kilometer. Webb's onboard computers and data processing systems can complete the initial analysis and formatting of astronomical observations in timeframes shorter than the time required for light to travel just 1 kilometer through space. This rapid processing capability ensures that scientific data can be efficiently prepared for transmission to Earth, while new observations continue uninterrupted. The processing systems can identify and flag potential anomalies, apply initial calibrations, and format data streams according to the requirements of different scientific instruments and observational programs. This computational speed is achieved through specially designed processors and algorithms optimized for the types of data analysis most commonly required for Webb's scientific objectives. The rapid processing ensures that the telescope can maintain its busy observational schedule while ensuring that valuable scientific data receives appropriate initial analysis before transmission across the vast distance to Earth. Each processed observation represents the marriage of cutting-edge astronomical discovery with advanced computational technology. Webb's mirror alignment can be adjusted to compensate for changes smaller than the thermal expansion of a single atom. The telescope's active optics system operates with such precision that it can detect and correct for dimensional changes in the mirror structure that are smaller than the thermal expansion of individual atoms. This capability ensures that Webb maintains perfect optical performance, even as its components experience the subtle thermal cycling that occurs during its orbit around L2. The alignment system continuously monitors the telescope's optical sophisticated wavefront performance using sensing techniques that can detect aberrations at the nanometer level. When minute changes are detected, the system commands the mirror actuators to make corresponding adjustments, maintaining the precise optical alignment needed for optimal image quality. This real-time optical correction happens automatically and continuously, ensuring that Webb's observations remain sharp and detailed throughout its mission. The precision of this system represents one of the most advanced applications of adaptive optics technology ever deployed in space, creating optical performance that improves rather than degrades over time. The telescope's communication protocols can transmit scientific discoveries using data compression more efficient than any terrestrial internet system. Webb's advanced data transmission systems employ compression algorithms specifically designed for astronomical observations, achieving efficiency rates that surpass the most sophisticated internet compression technologies used on Earth. These specialized algorithms understand the statistical properties of cosmic signals, distinguishing between genuine astronomical phenomena and instrumental artifacts to optimize data encoding. The compression systems can reduce transmission requirements by factors of 10 or more, while preserving all the information content needed for scientific analysis and discovery. This efficiency is crucial because every bit of data must travel nearly 1.5 million kilometers through space, making optimal use of the available communication bandwidth essential for mission success. The compression technology represents years of development, specifically for Webb's unique requirements, creating data handling capabilities that maximize the scientific return from every precious moment of observing time. Each compressed transmission carries discoveries and insights that would be impossible to share without these advanced encoding techniques. The telescope's power distribution network manages electrical flow with precision exceeding the regulation systems of entire cities. Webb's electrical systems control and distribute power throughout the observatory, with regulatory precision that surpasses the capabilities of municipal power grids serving millions of people. The power management computers continuously monitor hundreds of electrical parameters, adjusting voltage levels, current flows, and power allocation with response times measured in microseconds. This electrical precision ensures that sensitive scientific instruments receive exactly the power they need while protecting all systems from voltage fluctuations, current surges, or other electrical anomalies. The power distribution network can predict electrical demands based on planned observations and automatically configure itself to provide optimal power delivery for upcoming scientific activities. This sophisticated electrical management represents the integration of advanced power electronics with intelligent control systems, creating electrical infrastructure that operates more reliably and precisely than any terrestrial power system. Every electrical decision made by Webb's power management systems contributes directly to the telescope's ability to make groundbreaking astronomical discoveries. Webb's structural stability maintains mechanical precision better than the foundation of the world's most accurate scientific instruments. The telescope's mechanical structure provides a platform more stable and precise than the foundations supporting Earth's most sensitive scientific equipment, maintaining dimensional accuracy despite the thermal variations and mechanical stresses of the space environment. This structural stability is achieved through advanced materials engineering and thermal design that minimizes expansion, contraction, and mechanical drift throughout the mission. The structure must support the telescope's massive mirror assembly while maintaining optical alignment accurate to nanometer tolerances, a mechanical challenge that required revolutionary approaches to spacecraft structural design. Every joint, fastener, and structural element was designed to contribute to overall system stability, rather than introducing mechanical uncertainties that could degrade optical performance. The resulting structure provides a foundation for precision that enables Webb's most demanding observations while operating in an environment where traditional mechanical references simply don't exist. This structural engineering achievement represents decades of development in space-qualified precision mechanics and advanced composite materials. And now, as our gentle journey through the wonders of the James Webb Space Telescope draws to a close, let your mind settle into the quiet beauty of what we've discovered together. We've drifted through the extraordinary precision of mirrors polished smoother than any earthly surface, marveled at instruments that can detect the whisper of ancient light, and explored a telescope that operates in the profound silence of space with stability exceeding our finest laboratories. From its delicate sunshield unfolding like cosmic origami, to its ability to peer back through billions of years of time, Webb represents humanity's most ambitious attempt to understand our place in the universe. Each photon it captures, each spectrum it records, each discovery it transmits across the vast emptiness of space brings us closer to answering the deepest questions about existence itself. Tonight, as you rest, remember that this remarkable instrument continues its silent vigil in the darkness, collecting light that began its journey when the universe was young. In the precision of its mirrors, the sensitivity of its detectors, and the elegance of its design, we find not just scientific achievement, but a profound expression of human curiosity and wonder. If you found peace in these cosmic explorations, consider sharing this journey with others who might also find comfort in the gentle mysteries of space. Subscribe for more soothing science, and let the universe continue to inspire your dreams. Sleep well, knowing that somewhere in the cosmic dark, Webb watches and waits, ready to reveal tomorrow's wonders.